In this series of videos I've been looking at this ZAX ICD178 Z80 in-circuit debugging tool, and in particular in this series I will be developing some Windows software to control this. It's normally controlled through a terminal, a dumb terminal. You just send it commands through the serial port and that's how you control it. But this is an in-circuit debugging tool for Z80 processors. You basically unplug your Z80 from the target machine, plug this into it, and then you can control, debug, trace, do all sorts of things. That allows you to fault find and debug both software and hardware, and I'm going to be using it for several things. One is obviously for repairs, but in an upcoming series of videos I will be developing a Z80 computer from scratch, and it will be a full-fledged computer. It will have monitor output, cursor, the ability to run CPM, and we'll be designing that from scratch, and I'll be using DRAM, so all the things you would normally find in a vintage computer. And that's really why I wanted to get this working, because it will be quite useful for both myself developing that particular computer, but also it should make the videos more informative because I'll be able to show you the inner workings as we progress. So what I've got to so far is, when I received this it didn't work. I've had it for a while and finally got round to repairing it. Quite a number of faults, but it's now working, and so I've moved on to starting developing the Windows application I'll be using to control this. I could of course just use the terminal emulator to control this, but I wanted something a bit more visual to kind of streamline the process and make the work go a bit more quickly. So the one I've started with so far is I've put together the framework of the Windows application. We'll have a look at that in a few minutes, but just wanted to take this opportunity to show the types of things that you have to deal with when you're developing Windows applications for older bits of equipment. There are some kind of peculiarities that often crop up, and this is a good opportunity to show the sorts of things you're going to see. So my normal approach, I've written quite a few commercial applications, some very complex ones, including database, data acquisition systems, and my approach for commercial applications is different from when I'm writing something just for myself. I obviously don't want to go down the formal route of a white paper design and then the usual long-winded approach that you have to take for validating and testing a commercial application. But one thing that's common to both my commercial approach and something like this is, one of the first things I do is to get something put together, get some framework of the application, and that applies whether it's a software development, as we'll be looking at today, or a firmware development that we'll be looking at in future videos. I like to get something put together and get the framework of the application up and running, so I can get the inner workings of it sorted out before I start making it look pretty. The making it look right is the easy bit. Getting the inner workings to function the way you want is the first thing I like to focus on. So what I've done so far is put together the basic framework of the application, and I started off by hooking up my Fakerscope to the serial port, and the reason for using this is it allows me to send out a continuous stream of data to the serial port on the PC. The advantage in doing that is that unlike something like the ICD, which sends out data intermittently and also requires commands in order for it to do that, the Fakerscope will just continuously send data as an unbroken stream, and that means that you're kind of looking at worst case as far as the ability of your software to kind of figure out what's in that data stream. There are no gaps in it, so you can be sure you're not going to lose data when you start looking at something like the ICD. So I put together the framework of the application, got it so it could look at the individual data lines the Facoscope was sending out. So it does send out continuous data, but there are carriage return characters in there. And then I moved on, and that's what we'll look at now to see how far I've got with the application. Haven't got very far, but I'll give you some idea as to what I'm aiming for and how far I've got, and also look at some interesting bugs. Now, the two bugs we're going to look at today I have introduced intentionally. At least the second one I introduced intentionally. The first one had me scratching my head for a while, but it's quite interesting, so I thought I would show it. So we'll go across to the PC and have a look at the application. Okay, so I'm writing this application in C++ using Rad Studio, and this is a kind of visual Windows development tool, and I've been using this for quite a long time. It's one of my go-to methods for developing Windows software. It does have some peculiarities, but it's quite a powerful development tool. I can't show you the entire window because the YouTube video would be a bit too unclear if I try and get too much in it. So we're kind of zoomed into the center section, but hopefully you can see enough to see what's going on. So as I said, I tend not to worry too much about the visual appearance of the application when I first start. Also, I tend to drop things onto the forms I'm developing just for debugging and fault finding. So a lot of the things you can see dotted around here are just to help me with the development, but they will disappear once the application is up and running. And again, I'm developing this to suit what I want it to do. So if you're developing something similar, you might want it completely different, but because I know, roughly speaking, what I will be doing with this, I know what features I want. I haven't yet figured out exactly how they're going to be configured and how they will look, but the general features are starting to come together fairly quickly. So the first thing is I generated a main form, which we're now looking at. It's got a status bar at the bottom, and that enables me to show information about the current status of the application. Got a menu system that will grow as the application develops. But the first thing I wanted to do was to get the RS-232 sorted out, because trying to integrate a modern Windows application with RS-232 can be it's a bit trickier than it might first appear, partly because of the asynchronous way that Windows handles the system UARTs with regard to the Windows API. And one thing I've seen probably thousands of times in various forums is a particular issue that can come up when you're trying to write Windows applications that use the RS-232 port. So I've intentionally created a bug in this application that normally I would just design out right from the start, because I'm aware of what causes it, but I thought I'd show this because it's something you might well see if you're not aware of the issue. Now, with firmware applications, I never buy libraries. I always write things from scratch. But with Windows, it's slightly different. I have in the past bought a couple of object libraries. And one of those is one for serial communications and USB communications. And to use this, you really just drop one of the objects onto the form, and then you can access its various settings. Also, one thing I'd point out here is that while most people, and even in my own commercial applications, I use the Windows registry to save data and settings, when I'm writing applications for my own personal use, I still use INI files to store the information, just because for me it's much easier to do that, and I can chop and change it and manually make changes far more easily than using the registry. So the first bug we're going to look at is a very common one, and it's caused for a very particular reason that I'll explain as we go through this. But if I try and build and run this application, I've also got an introduction screen, by the way, that you just saw pop up. Notice that this started up quite nicely. We've got the application. We'll come to what it does in a few minutes. I just want to show this bug first. So I'll shut it down, we'll restart. Seems to be working. and each time I start it there appears to be no problems. But if I try and get it to do something, again we'll come back to the application and what it's currently doing in a few minutes, but notice this time when I try and run it we get this error, and this is a very common error that you'll see in a lot of forums, and it says device, then the COM number, open error, access denied. So we'll close that, try and run it again, and this time it starts. And that's random. Sometimes that'll pop up 50 times in a row, and other times it might run and start 20 times without issue. And as you see, it comes up randomly. Now what's causing that is when the application starts, the object that's trying to basically get hold of the COM port is checking the status of the UART, and if the UART is showing that it's busy, that is if the UART's saying that it's got data in it, then the application is not allowed to grab the COM port, and you'll see that error message popping up. Now normally what's causing it is because the application is trying to effectively reset the UART at the same time as the application starts, and normally it results in 1 or 2 bits of data appearing in the UART, and that basically flags the UART as being busy. You'll notice this if you plug a serial cable in while a terminal program's running, you'll see kind of rogue characters appearing. It's the same sort of thing when you start an application, the same thing happens, but at the electronic level rather than the hardware level. And the way around this is, what's causing it is the object that's trying to access the UART is active at the same time as the application's trying to start up. So the way around this is to disable the UART object, the object that's trying to get hold of the UART, so that the application's not actually trying to access the UART when it boots up. And then in code, after a delay and after the application started, is you then enable the object that's trying to access the UART. And if we now rebuild this, we won't see that error message anymore. It'll permanently go away. So that's what caused it. It's just because the UART behavior is asynchronous with the Windows API, and if you try and have the UART access occur at the same time the application's booting up, that message, that error may randomly appear. So to get around it, just separate the two, have the application start, and then enable access to the UART. So that was the first one. That was fairly easy to deal with. In fact, I introduced that on purpose. In fact, I had this connect function that normally I would use. I've disabled it now because I don't want to have to go across to the side of the room where the ICD is each time I start up the application, so I've just bypassed it. Now the other bug is far more difficult to track down. It was quite strange, and I have dealt with it, but I've kind of reintroduced it so you can see what's going on. But in order for me to demonstrate it, I need to kind of start up the ICD and show you how this is working. So before we start, just a quick outline of the current application. Most of this information down here you can ignore, might well change as we go. But what we have is a series of menus. Setup just allows me to set up the COM port and configure it as I need to. And the other ones are just general setups to allow whether the application can change the Z80 registers in the ICD. And the other ones are just preference settings to change things such as the color of the console window, etc. That's the sort of thing that I just put this in here, just a few things in there at the moment, but that's just so that I have the general makeup and layout of the application sorted out at the beginning. The more interesting parts are the windows that I'm including that will really give me access to the commands in the ICD. So for example, if we come into view, we can look at a window that shows the CPU registers. Now before this will really work, if I try and open this now, you'll see it'll come up, but it won't really do anything. And in the console window, we're getting these red characters showing up. So the black console window is really everything going to and coming from the ICD through the RS232 ports, especially everything that's been transferred between the two. Anything in red is being sent from the application. If it's in green, it's coming from the ICD. Notice there's no response from the ICD, and that's because the ICD is currently switched off. So I'll go and switch it on, and we'll see if that makes any difference. So I've switched on the ICD, and as you can see, we're getting the welcome information. This is why I changed the ROM code in the ICD, because I wanted to see this in this tool to make sure that it was properly connected. So we can see that we are receiving data. It's in green, so you can see that we're properly receiving the data and able to make sense of it. And if now we open the CPU registers window, several things happen. The first thing is the application sends the R command to the ICD asking for the register information, and the ICD in theory should respond, and so we should see that in both the console and the registers window itself. So if we open this, notice we're getting the information coming through the console. We've got the red R because we sent the R command to the ICD. It echoes it back, which is why we're getting this green R, and then we get the actual register information. And this is again in green, so it's coming from the ICD, finally followed by the command prompt from the ICD. Notice now that the CPU registers window has come to life. I've laid this out in a similar way to the layout of the registers as they're shown in the data sheet for the Z80, just because I prefer that layout, and it seemed to make sense. Notice some are in green. What I've done is anytime the current register value returned is different from that from the previous time we retrieve the register information, it shows as green, so it's very obvious when any have changed. And we can now update this. Because none have changed, they've all gone to white. And I can change any of these that I want to, so we can either click on the flags to change the flag status. Notice that the flag value is also changing. Or we can send a value through to the ICD. So if I want to change the value of the A register, I can just type it in. It then automatically sends the command to the ICD, and the ICD echoes that back. If we now refresh, notice here we've got the value for the A register, and that has now changed. And we can do the same thing with any of the other registers. If I want to change this one to 55 for the B register, again, similar sort of thing has happened, and now we can retrieve the information, and the B register value has changed, and that's reflected up here. Just clear the console. So we can change the registers as and when we want to. The two values down here are the value that is currently being pointed to at the stack. It's not the stack pointer value, it's what's at that address, and the next instruction value that's returned as part of the registers command. So this is working fine. What I'm going to do now is just, I only have a few of the features working so far, so to really get this working properly and show you the second bug I was talking about, I just need to configure the ICD, but at the moment I have to use a terminal program because I don't have the rest of the commands active yet. So I'll just close this down. What I'm going to do is send a test file that we've seen before to the ICD, and then set a breakpoint and the trace options. Okay, so I've sent a file to the ICD that contained the test program we looked at before, the memory test program. I've set the breakpoint at the same point we used previously, and I've set trace to all. If we now run the application again, what we can now do is load the CPU registers, and again, same sort of thing, they've still got the same values in, although I've loaded a file, it hasn't changed the registers. And I can now also open the breakpoints window. Again, this layout is just temporary, it's just so I can see if the underlying structure of the program's working. And if we click on update, we can download the current breakpoint settings. So I've got the breakpoint set, hardware breakpoint set to 401C, and again this is reflected in the data that comes through into the console. And what I can now do is run that test program. So if we set the starting address, click on go. So it's working, kind of, and if we now click on the history, it's showing us the disassembled version of the code that was traced. So this is what was traced through when we just ran the file we uploaded. You can see it's shown as a very nicely laid out file. And what I'll be doing with this is allowing, you can modify this and edit it if you want to whatever you want, and then I'll be allowing this to be sent back up to the ICD or saved to a file. So it'll be a very powerful tool. If we want to make small changes, then it will allow us to do that, rerun the application and see if it's working. Or we can look at the same history in terms of machine cycles, which again might be useful depending on what we're doing. So again, very powerful tool already, but notice over here there's something wrong. And this took me a while to figure out what was going on with this. It started showing this, but it doesn't do it if you look at something like the register command. So if we clear this, and I click on update registers, it's fine. We're not getting this weird prefix to the data. But if I run the application again, we're getting this, and if you look at it, it's the same information repeated twice. In this case, it's saying form 1 console, form 1 console, and then the actual correct data. But the data coming in must be correct, because when we look at the history, we're getting the correct information. And in fact, if we clear that and click on history, you can see the information coming back from the ICD is correct. So there's something strange about the go command that's causing it to return this odd prefix to each line. So this looks for all the world like a buffer overrun. If you're familiar with writing Windows software, you know if you don't properly reserve memory space for certain objects, it can cause this sort of weird behavior. But looking at it, it turned out not to be that, and in fact I tried rebooting the PC and it stopped doing it for a few minutes, and then it started doing it again, and finally the penny dropped and I realised what was going on. And it only does it for the go command at the moment. That's the only one I've seen it do this for, but as it turns out it would do it with other commands. But to get some idea as to what's going on with this, if we close the application and I go to the part of the application that's looking at the incoming data, and if we run to that point, so if I now go to the same point, if we look at the RX data text, which is the buffer for the incoming data, notice we're getting form 1 console, we're getting that same text appearing, which is kind of strange. But if I run back to that same point again, this gives away what's actually happening. And this, the reason there's a lot of data in it now is because we're not handling it in real time, so it's kind of buffering all the incoming RS-232 data. So we're seeing now all the data that came in response to the command that we sent. And if we look through it, if you remember, we're getting 2 repetitions of that strange string. And if you look through this, it's obvious what's going on if you're aware of how Windows operates. So what I'm going to do is run back through to the same point. In fact, I'll get it to finish off what it's doing, and then we'll go back to the same debug point. Notice it's got this nonsense now. But I'm going to make a change. I'm not going to show you what it is. I'm not going to change the software. I'm not even going to restart the application, but I am going to just do something off camera. Okay, I've done something off camera, but I haven't changed this application. I haven't changed anything in Windows. I haven't really modified anything. But if we now rerun this, clear the console first, rerun this fact, I'll just run it so you can see what's going on. So I'll do that again, but I'll just run it from scratch without halting. Notice now this text has changed. So whereas it was saying something before repeated twice, it's now saying something repeated twice, but it's different text. And finally I figured out what was going on, and this information, that text repeated twice. And what this is, it's information that's currently on the Windows clipboard. So what I did without showing you just now was to cut and paste this text into the Windows clipboard. Shouldn't be putting here, of course, but this is one of the things you get with vintage equipment because of the historic way that certain functions within Windows and certain character values have special meaning. And so if you get a serial data stream, for example, you can get odd behavior. Now if we pause the application and we go back, so first time through we're seeing the return string from the ICD. We'll go back round and now we should have got a lot more information come through. But if you look along the text that's been received, you see this character here. So the /x and then a number is, it just means it's a hex value. In this case, hex value 16. And if we look along, it's here as well, x16. So it's basically saying there's a hex value of 16 coming through in the data stream. You don't see it on the terminal, the console window, because it's a non-printable character. But that is used as a control character in a serial stream, but Windows interprets that as a control V. It's exactly the same character, and control V in Windows is obviously the paste from Clipboard. Now it shouldn't be doing it, but for whatever reason the object that's being used as the receive data terminal for the object we're using for the serial communications is interpreting that control V to mean paste the data from the clipboard into the data stream, which it's not supposed to be doing, but it's doing that anyway. So to get around it, there's a fairly easy workaround. What I'm going to do is change the terminal object I'll be using so it doesn't accept pasting from the clipboard. But for now, an easy workaround, as you can see, I've already put it in, but I disabled it just to show you this, is to clear the clipboard at the start of that particular function. So if we now come back in and we try and run this again, notice it's cured the problem. So it's got rid of that weird text. And it's not just because there's nothing on the clipboard. If I cut and paste something to the clipboard, and then we try and run this again, it's still not there. Everything else still works the way it should do, but we're just not seeing that rogue data. So it's weird things like that because of the nature of the way that Windows interprets certain characters that you have to be aware of. And now of course we've got this full access to the functionality of the ICD. So this is the approach I'm taking. It gives me a good visual indication as to what's going on. I can download the captured data, I can edit it, I'll be able to send that back up to the ICD. I'll be able to do that in terms of saving it to a file, making small modifications, and it will give me a lot more control over what the ICD is doing. I'll even be able to just write code into a new window and have it assembled or compiled depending on what your preference is and sent up to the ICD, and it will give me what amounts to a fully fledged integrated design environment for the Z80, and that will allow me to control both firmware, software and hardware development seamlessly from within the application. So the other sorts of things we've got in here are various buffers. So if we want to look at the trace buffer, send commands, watches, breakpoints, memory map. So I'll be able to define the memory map from here just in a visual way. and it'll work in the same way as the CPU registers, that when you change something it will send the appropriate command up to the ICD, refresh the image, and I'll be able to save all the settings into a script file. And so we'll have a script, and this will allow me to create a series of serial commands that you can save to a file, and when you load it, it will configure the ICD appropriately by sending all the commands out in sequence and give you an easy way to reconfigure the system. So that's where I am at the moment. You can see that the underlying structure is starting to come together. It's going to give a fairly powerful tool for developing systems, hardware and software, firmware for the Z80, and give me very good usage of the ZAX ICD. Okay, comments welcome. If you've got any particular aspects of the system you want me to go over, I won't be showing too much code. I'm not trying to hide it, it's just that it's probably fairly tedious for you to work your way through all this. But if there's anything in particular you want to see, let me know. It is of course split into various modules, so there's currently about 10 or so, but there'll probably be 30 or 40 by the time I've finished. Most of it's fairly repetitive because this type of application is just accessing different objects but doing fairly similar tasks to them. The code's not too complex yet. It will get fairly complicated, but as I say, if there's anything in particular you want me to go over in terms of the way that the application works, then please leave a comment, and if I get any more interesting issues popping up, I will of course cover those, and I'll post some regular videos as to the progress, and then ultimately we'll move on to developing our Z80 computer.